Bismillahirrahmanirrahim. Hi everyone. I hope you are all doing well. I am Azmat Ali and I welcome you all in class of elementary number theory. We are using here uh, elementary number theory by David and Burton. In today's lecture, we will discuss from question number 3 of problems 1.1. Question number 3 is use the second principle of finite induction. We have to establish the following formula for all positive natural number greater than 1. That is a raised to power n minus 1 is equal to this. We suppose the given statement is denoted by Pn, then the base step, we firstly check the statement for n is equal to 1. Let Pn be the given statement. Our first step in second principle of finite induction is, that is the base step. In this step, we check the statement for n is equal to 1. Here, statement for n is equal to 1 is P1 such that we put n is equal to 1 in the left hand side of the given expression. We have a raised to power 1 minus 1, and similarly when you will put n is equal to 1 on the right side, you have a minus 1 into a raised to power 1 minus 1. We will not put n is equal to 1 in the next terms, because for n is equal to 1 we will consider only those power of a for which the exponent is non-negative. So here, from here you can check that this become a minus 1 and this is also a minus 1, because a raised to power 0 is 1. So the left hand side is equal to right hand side. That shows the expression is true for n is equal to 1. Next we move towards the inductive hypothesis. That is the second step. Inductive hypothesis. In this step, we suppose that the given statement is true for n is equal to k. Because we are using here second principle of finite induction. In second principle of finite induction, we suppose that the statement is true for n is equal to k and all the preceding integers for k, from k. That is, suppose that the statement is true for n is equal to k and all the preceding integers, then k, such that the statement for n is equal to k is given by substituting n is equal to k in the given expression. We have a raised to power k minus 1 is equal to a minus 1 into a raised to power k minus 1, a raised to power k minus 2, a raised to power k minus 3, up to so on a plus 1, and statement for n is equal to k minus 1, k minus 2, up to so on statement for n is equal to 2, p of 1 are all true. Suppose we say this is our expression number 1. Next we will show the statement is also true for n is equal to k plus 1, and this step is called inductive step. we show that pk plus 1 is true whenever p1 p2 up to so on pk are all true. What is the statement for n is equal to k plus 1, where the statement for n is equal to k plus 1 is given by, if we substitute here n is equal to k plus 1 on the both sides, we have ak plus 1 minus 1 is equal to a minus 1 a raised to power k, a raised to power k minus 1, a raised to power k minus 2 up to so on a plus 1. Say this is question number 2. To prove the truth of pk plus 1, we will take the left hand side and use the expression number 1. Okay, now we take the left hand side of the expression, that is ak plus 1 minus 1. Next we add and subtract the term ak to involve expression number 1 here, ak plus 1 by subtracting ak and adding. From the first two terms, if we take ak as a common, this becomes a raised to power k a minus 1, and from the last two terms we write it as a raised to power k minus 1. This is a raised to power k into a minus 1. Now by using expression number 1, from expression number 1, a raised to power k minus 1 is equal to this. So by substituting the value of ak, a raised to power k minus 1 here, we have a minus 1 into a raised to power k minus 1, a raised to power k minus 2, a raised to power k minus 3 up to so on a plus 1. From these two terms, we take common a raised to power minus 1. Remaining expression is a raised to power k, a raised to power k minus 1, a raised to power k minus 2, a plus 1, which is equal to the right hand side of expression 2 that we have to prove. This shows that the statement pk plus 1 is true whenever statement for n is equal to k, k minus 1 up to so on 2, 1 is true. Hence, by second principle of finite induction, statement is true for all n greater than equal to 1. Pn is true for all n greater than equal to 1. In this question, you can solve, you can use the induction of k and k minus 1 both. This is an alternative method to solve the question. You can involve the induction. I am using only the induction of k, and remaining I am using the truth of the statement for all preceding integers. If you want to use the induction of k and k minus 1 both, then you can also solve this question. Next we move towards the question number 4. That is a very interesting question. In question number 4, we have to prove that the cube of any integer can be written as the difference of two squares. For example, we can write cube of 2, that is 8, as a difference of two squares, like 3 square minus 1 square. If we consider the cube of 3, that is 27, this can be written as the difference of two squares, 6 square minus 3 square, 36 minus 9. So in this question, we have to prove the cube of any integer is actually the difference of two squares. I will solve this question by two methods. Method number 1. Let n be an integer such that the cube of n is the difference of two squares, a square minus b squares. So now my target is find the values of a and b in term of n. We further can it write as a minus b into a plus b. On the left side, we write it n into n square is equal to a minus b into a plus b. From here, I set a minus b is equal to n and a plus b is equal to n square. You can observe this setting by a particular example. From this, you can write it as 6 minus 3 into 6 plus 3, and this is 3 raised to power 3. If you observe here, 6 minus 3 is equal to 3. This is my a, this is b, and this is n. So we can write a minus b is equal to n here. You can verify this also from this example. If you write it as 3 minus 1 into 3 plus 1, this is a minus b and this is a plus b. And you can write it as 3 minus 1 is equal to n, that is here 2. So we can set this it as a minus b is equal to n and a plus b is equal to n square. This is my question number 1 and this is my question number 2. From these two questions, we will find value of a and b. Okay. By adding 1 and 2, we have a minus b, a plus b is equal to n square. This becomes 2a is equal to n plus n square, and from here a is equal to n square plus n by 2. Further, we can write it as n into n plus 1 over 2. And substituting this value of a in one of the equation, suppose we substitute this in equation number 1, we have n square plus n by 2 minus b is equal to n. From here, n square plus n over 2 minus n is equal to b. b is equal to n square plus n minus 2n over 2. From here, b is equal to n square minus n by 2. You can write it as n minus n by 2. Finally, substitute these two values of a and b in star. We have n cube is equal to, what is this? This is equal to a square minus b square. What is a? A is this, n into n plus 1 by 2 whole square minus, what is b? N into n minus 1 by 2 whole square. So you can see that we can express the cube of any integer as the difference of two square from this formula. This formula is hold for any integer n. Further, if you want to to prove the validity of this formula, further you can use mathematical induction and verify this formula. Now I discuss the second method to prove this. Now I am going to discuss the method number 2. Actually, this hint is available in your textbook of. We know that the sum of cube of first n natural number is given by 1 cube, 2 cube, plus 3 cube up to so on n cube. This is the sum of the cube of first n natural number. This is actually given by n into n plus 1 by 2 whole square. This is my equation number 1. Similarly, if we consider the sum of cube of first n minus 1 natural number, you can write it as n minus 1 cube. In the right hand side, we just replace n is equal to n minus 1. So this becomes n minus 1 into n by 2 whole square. This is my equation number 2. Because this is the sum of first n minus 1 sum of cube of first n minus 1 natural number. So we just replace here n is equal to n minus 1. This becomes n minus 1 and this becomes n. Now subtracting 2 from 1, we have, when we subtract the left hand side, we have only one term, that is n cube. This is equal to n into n plus 1 over 2 whole square minus n into n minus 1 by 2 whole square. That is the same as previous. So I hope now you have a clear understanding about the lecture. Inshallah, in next lecture we will start from question number 5. Okay, take care. Allah Hafiz.